we actually probably should take a break and then come back and fill in the missing pieces. Because not every function exists over a time of exactly 2 pi. So we have to deal with that. All right, let's take a 5-minute break. I'm going to pause this and pretend that I'll remember to turn it back on. There we go. All right, so at the top, I'm going to start out with a cosine curve, because actually in terms of context of what we will be doing, cosine will pop in more often, generally because if I take a spring and I pull it down and I let go, we're starting at the maximum already. And so it will, cosine curve eliminates one hassle that we'll have later. So we do have the cycle, so if we start with cosine, then if that's my position graph, my velocity graph's negative sine, my acceleration graph's negative cosine, my jerk is sine, my snap is cosine, crackle, pop. It just cycles through in terms of slopes. All right, so y is equal to the sine of cosine of t. That's the basic cosine curve right there, and it ends at 2 pi. So if I do cosine of 2t, what does that do to my graph?
It flips it.
It does what?
It flips it. Instead of being in the negative, be positive slope.
Oh, now in order to flip it, I need to put a minus sign in front.
Okay.
2 does not flip it.
It's going to shrink it.
If you think about on a graph, if I've got a wheel here that's spinning around, so if I start at the maximum position and just look at the projection onto a vertical axis, so what I'm picturing here is I got a wheel here and I got a peg in it, and I got a bright light shining on it, I'm going to cast a shadow. So if I start with it at this position right here, my shadow starts at that point, and as the wheel turns, the shadow is going to be basically moving up and down. If we plotted that in terms of time, it would look like this, if we started at the top. 2t is we're now spinning the wheel twice as fast. In terms of the speed of the wheel, that 2 would be considered the angular speed. In terms of the plot, in terms of this is known as the angular frequency. The difference between angular speed and angular frequency is context. They look and smell the same, they have the same units. I have not run into any situation where you have angular frequency and angular velocity or angular speed, which could not be used interchangeably. All right, so twice as fast, which means that it's got to be done by the time we get to pi. Let's see if I can find a better red marker. Let's see how things do it today. It looks pretty much the same. And then it repeats itself again. You could also look at this as where I used to do just 1 trip around, I now do 2. So it's going twice as fast. I get 2 cycles here within the space of 2 pi. What does that do to my slope?
It makes the slope steeper.
Yeah. Matter of fact, it makes it twice as steep. So if this goes from 1 to -1, and this goes from 1 to -1, then what that does is, if I do the slope, so if this is my position graph, my velocity graph, well, if this is cosine, my next step down is negative sine, so it's basically going to look like this. Oops. Try that again. And this is going to go from 2 to -2. So whatever number I have there, basically, it's a multiplication factor of what the slope is going to look like. So now I've got a graph here that is twice as long this way as it was before. What is that going to do to my acceleration graph? Not going to squeeze it that way from a math point of view. Not going to shrink it that way. So if I take a graph here, doesn't matter as long as there's a curve in it. And now I make it within the same time frame. I make it twice as tall. Making it twice as tall does what to the slope?
Twice as fast.
It makes the slope twice as much, twice as fast. It depends upon how you want to look at that. So my acceleration graph is going to go from 4 to -4. Matter of fact, each time you go down, whatever number right here, you're going to just multiply that out front. So if my position graph is a cosine of t, I'll switch back to x, cosine of 2t, sorry, my velocity graph is going to be -2 sine of 2t, and my acceleration graph, I multiply again, so -4 cosine of 2t.
And you just keep multiplying by 2 every time.
Yep, because of that number right there. And there are two other things that we can do, actually, three other things that we can do to this function. We can change the amplitude. When I say amplitude, what am I talking about?
The height.
Okay? So if I just started out with something that was twice as big, so why don't we start out with y is equal to 2 cosine of t. So I have no number right in front of the t, so it's going to take 2 pi is basically how is the cycle length. So 1, 2, 1, 2. So cosine starts at the peak, so that's 2, -2. That's 2 pi. So by starting out with it stretched out, what does that do to the slope?
Speeds it up.
Okay, or makes it bigger.
Makes it steeper.
I feel like you're in a rut there with speeds it up every time.
Yeah. I just think slope skiing speeds it up. Just
It will speed it up, and physically what's going on there is, I started out stretched like this, and I started out with its equilibrium position, I pull it down, and it goes up and down. I now stretch it twice as far. It's going to have to move twice as fast as soon as I let go. And so if my position graph is 2 cosine of t, my velocity graph is -2 sine of t, and my acceleration graph is -2 cosine of t. I'm not multiplying it every single time. That's the big difference in the effect. So we're about to put those two things together and then talk about the last two changes that we can make to this.
So the number in front of the cosine or sine makes the amplitude higher,
Yes.
but the number in front of the t makes the time shorter, or makes the frequency higher.
Yes. So if I have a position, I'm modeling a position with the following equation. 4 meters. we'll leave the units off for right now. 4 times the cosine of 3t. My velocity graph. Well, first off, cosine goes to negative sign. So I got a negative sign here. That 3t stays, but up front, I've got my 4, and then I've got this 3 from here, so this becomes 12. Because when I had it next to the time, I multiplied it every single time. When I had it out front, the amplitude, that just stayed out front. My acceleration, negative 36 cosine of 3. Now my acceleration is not exactly like my position because I got a different number sitting out front, but I still have cosine 3t here, cosine 3t here. But the fact that these are different is okay because I've got k and m, which are going to offset that. Questions to hear before I bring in the last 2 things that you might see in these equations? All right. The 2 graphs that we started with a sine, we started with a cosine. Sine starts at 0, cosine starts at the peak, or if it's negative cosine, at the trough, but they both proceeded from there. Now, if I'm actually filming something, so if I take this spring, I have a motion sensor underneath it, I have something on the bottom so the motion sensor senses it, and then I have this thing go up and down, what are the odds that you're going to start the timer or start the motion sensor at the exact same time that this is at the peak or at 0?
Very rarely.
So in reality,
It's an approximation.
we might like to see that happen, but reality is it's not going to start like that. It's, it's going to be a little bit off. In other words, the graph is going to shift left or right. This is why we have the phase shift. Now, if I shift the graph left or right, how does that affect the slope?
It doesn't affect the slope. It doesn't affect the slope.
Right. So phase shift is something that gets tacked on. It does not affect anything other than the fact that it still shows up. So the phase shift is basically added here. So plus, it really doesn't matter, 7. All it's doing is saying where we're actually beginning. So this is called phase shift. So the number up front, amplitude. The number in front of the t is the angular frequency. And the number at the end is the phase shift. And the last bit, I take my graph here and I've made the assumption in all the ones that I've done so far that 0 is that equilibrium position, that it's just natural resting places right there, that's 0. But if I have a motion sensor down here, unless you fix it otherwise, this is not 0. 0 is going to be down there near where the motion sensor is by default. So by shifting where 0 is, what you're doing to the graph is just shifting the graph up or down. So if it doesn't start at 0, if you have a motion sensor down below it, it might actually look like this instead of down here. What does that do to the slope by taking the graph and moving it up like this?
Again, it does nothing.
And so that's a number that gets tacked on the outside. I've already used 4, so plus 5. It does not affect my slopes, does not affect what my velocity or acceleration is. And I'm really not quite sure it has a special name, but if you're using the LabQuest, it'll give you a number.
LabQuest?
Pardon?
LabQuest?
I'm assuming you've used LabQuest.
Don't know.
One of these?
And a PDA?
No, not a PDA. You have not used this?
No.
Nope.
Oh, you did 131 online?
Yeah.
Yeah.
Ah, okay. At some point, you'll get to use this. You hook it up to a motion sensor, and then you can actually, it will plot where it is with respect to time, then you do a little curve fit, and it will tell you, oh, you want to plot a cosine function? Okay, it will give you this, and this number. It'll tell you the amplitude, it'll tell you the angular frequency, it'll tell you the phase shift, and then it'll tell you the vertical shift. Okay, sorry about that. That whole pandemic thing, still throwing me. It's once you start to use it, you'll pick it up quickly. It's not a complex thing. Unless you touch the screen at the wrong time, and then it'll blow up.
Well, I never use that, but I have used it. Won't make it work. I'm gonna be an electrician, and I don't remember the name for it.
For what again?
The frequency of AC circuits. I
Oh,
don't remember what they're called.
Hertz?
No, it's a tool to measure it. You can see the frequency of an AC circuit.
Oscilloscope?
oscilloscope?
Oscilloscope, yeah, that's it.
Yes.
Okay.
I've used one of those, but I've not used.
I find this a whole lot more intuitive than oscilloscopes. So if you've done oscilloscopes and understand them, then this will be absolutely no problem at all. The difference is that when I turn on the oscilloscope, basically the picture is boom, it's right there, and here you can potentially see it actually plotting as you go, which to me gives it a much more tangible reality than oscilloscope does. And also oscilloscopes, at least the ones that I've used, didn't have numbers. You just had to sort of understand what it meant.
Well, the modern does.
Yeah.
The ones that we,
It's been a while since I've used one.
the ones that we have used do have numbers, but you have to know what you're doing to really, to do it correctly.
Okay.
Yeah.
So this potentially will take some of that fun out of trying to figure that stuff out. This was designed for pretty much any student. All right. Now, we're gonna solve this using just generic letters, sort of an alphabet soup. I'm gonna say that my position graph is equal to some amplitude times the cosine of omega t plus phi. I am going to assume that position is zero at its equilibrium position is zero. Again, this is an omega, and that equals the angular frequency. This is written down there, I'm writing it again. Yes, I am. This letter right here is phi, and that is the phase shift. Most textbooks will use, well, pretty much all the textbooks I've seen will use omega for angular frequency, and almost all of them will use phi for phase shift. Here's the cleverness of physicists when they do this. Phase shift starts with a f sound, and so therefore, what Greek letter starts with the same? Oh, phi, let's use that. That's basically how it goes. And if it doesn't seem to match in English, it probably matches in German or Greek. I think the P for momentum that is often used is from, I think that's from Latin. I keep forgetting, I saw it once what P stood for. And then A, amplitude. So if that is my position, my velocity is, well, I got my amplitude out front, and I'm gonna multiply times whatever that is, so that's A times omega times the cosine of omega t plus phi. So I just multiply that number next to t, and then I'm gonna do it again. Oops, messed up there, that should be negative sine. And then acceleration, negative A omega squared cosine omega t plus phi. So each time I go down, each time I do a derivative, each time I do the slopes, I'm going to multiply times the angular frequency. Now let's do a derivation. Now the reason that I do derivations is rarely am I doing it because I want you to regurgitate it later. The reason I do the derivations is I want you to see where this comes from. The fact that there is some logical path that goes from the stuff that you know to the new stuff. As opposed to, here's the situation, boom, here's the equation, without any explanation of how we got there. And so that's one of the reasons I'm doing this. So if I plug my acceleration in there, that becomes m times negative a omega squared cosine of that stuff equals negative k times my position graph, a cosine omega t plus phi. There's a built-in assumption here that my initial position is 0.
Now what's the squiggly line in parentheses?
I just didn't feel like writing it, but I should probably omega t plus phi.
Okay, that's what I was wondering. T plus equals.
So we start out with the premise that Hooke's laws are being obeyed. We get to here because this is a function that works. And now let's get rid of stuff. What can I cancel out?